So change in width we'll see in the next class. After we see change in width, we can also have combination of both hump and change in width. Okay, we can have combination of hump as well as change in width. Okay, so when there is a hump, if you have a particular channel, some discharge, some depth of flow, other geometry are given. Now, suddenly you provide a hump. Okay, hump is the bed is coming close to the water surface. Okay, and if there is a negative, we can also have a negative hump, which is basically a drop. The bed is going down. Okay, away from the water surface. In both the case, the change in the specific energy will be there. Okay, how the specific energy will change? We know the specific energy is measured from the channel bottom. If at a particular situation, specific energy is measured, say 1.2 meter. Okay, that is 1 meter 20 centimeter and 1.2 meter. Now, if I provide a hump of say 10 centimeter, okay, 10 centimeter, then what will be the new specific energy? The new specific energy will be 10 centimeter less because the datum has gone up by 10 centimeter. Okay, so 1.2 minus 10 centimeter or 0.1 meter, the new specific energy will be 1.1 meter. That is pre-hump specific energy is 1.2 meter and post-hump specific energy will be 1.1 meter. So you will be equating. But what about the discharge? If it is a rectangular channel, unit discharge or a trapezoidal channel, the discharge is not changing because you have just provided the hump. You are not taking the water out or there is no side track. Okay, so the same discharge will flow now, but the specific energy has changed because the bottom you have changed. Okay, because the bottom you have changed. If 1.2 meter specific energy and you provide a drop of 10 centimeter, then post drop or the downstream, the specific energy, new specific energy will be 1.3 meter. It will be more by, see, if I say delta Z is the hump height, okay, then new specific energy E dash is equal to E minus delta Z. New specific energy E dash is E minus delta Z. Okay, so this is your expression. E dash equal to E minus delta Z. Fine. Now, if delta Z is positive, it's a half. If delta Z, yes,
It's occurring, now it's occurring, sir. Yeah. It's okay, sir. It's
anyone
okay, sir.
say
Now it's
something?
occurring, sir.
Yes.
No, sir. It's okay. It's okay, sir. It's okay, sir. It's okay, sir. It's
Okay.
okay.
E dash equal to E minus delta Z. If delta Z is positive, obviously E dash will be less than E. But in case of drop, delta Z is negative. Say 10 centimeter drop means delta Z is minus 0.1 meter. Okay. So E minus delta Z will be more than E in that case. Okay. E minus delta Z will be more fine. And you will have a larger value of uh, uh, specific energy. Okay. Now, specific energy also changes when there is a change. Okay. You have the expression for specific energy. You have the expression for specific energy. You have E equal to y plus q square by 2ga square. Now, what about the new specific energy when there is a change in width? When there is a change in width, okay? When there is a change in width, A is a function of y, and hence with A with a with a change in width, A will change and there will be a new. What about the specific energy? Specific energy is not changing because the channel bed in case of change in width. In case of change in width, so specific energy will not change. But now new y, the y will change to y will change to y dash. Okay, fine. So with this, the new depth of flow y will change to y dash. Fine, but there is no e dash here. There is no e dash here. What about when there is a hump? Since e is changing e dash, y also will change to y dash. So in case of hump, e will change to e dash and y is changing to y dash. Okay. In case of change in width, in case of change in width, you will have only y changing to y dash. So it is matter to us that the depth of flow is changing. The depth of flow is changing. Okay. So if it is a rectangular channel, I can simplify this expression, specific energy expression for the rectangular channel only. Okay, for the rectangular channel only. For rectangular channel, you have E equal to y plus, so here I'll have small q and this one will be y. Okay, so this is the expression for simplified expression for rectangular channel, where q is equal to q by b, isn't it? So your small q is equal to q by b. Fine. So q is equal to q by b, and we have made use of this for a rectangular channel. So the cases y is changing to y dash. So now consider a subcritical flow. Okay, let's consider a subcritical flow. So now we will be concentrating for harm. Okay, for harm, eta c is E minus delta z. Okay, now there can be two cases. We'll consider subcritical flow and supercritical flow separately. We'll consider subcritical flow and supercritical flow separately. Okay, so in the subcritical flow, that is refer to the specific energy diagram. Refer to the specific energy diagram. If I bring your specific energy diagram. Okay. So what about the upper limb is the subcritical flow. You can see the upper limb is the subcritical flow. Fine. So in the upper limb, for a given specific energy, you have say R dash. This is the flow depth which is obtained. For any specific energy, there can be two flow depth, possible depth, R and R dash. One is subcritical flow, one is supercritical flow. Okay. One is subcritical flow, one is supercritical flow. So in the subcritical flow, if there is a hump and new specific energy, so it's a hump, delta is positive, delta Z positive, then new specific energy will be less than the original specific energy. So what happens? The specific energy reduces, that is, we move towards left, and we find that the point R dash will now come close to the critical depth. That means as the hump height will increase, from R dash you come close to C, then close to C, then close to C. Okay, and maximum hump height of E1 minus EC. E1 minus EC. Whatever E1 is more as compared to EC. Say E1 is 1.2 meter, EC is 1 meter. So 0.2 meter hump height will bring it to the critical flow. And if it is a 0.3 meter hump, then the specific energy of 0.9 meter cannot be supported with this discharge, because the discharge will have to have minimum specific energy of 1 meter. So 0.9 meter is not acceptable. Okay, so what happens? These are undesirable situations. We'll see what happens to that. So now two things we should see: subcritical flow and supercritical flow. Subcritical flow and supercritical flow. Subcritical flow, the flow depth, a new flow depth, y dash is new flow depth is less than y. Okay, new flow depth is less than the original flow depth. What about in the supercritical flow? In the supercritical flow, if we check, sorry, supercritical flow, as you move towards left, the flow depth is increasing. See the bottom limb, supercritical flow. So the situation will be reversed. Okay, situation will reverse. Y dash will be greater than y. Okay, so we should know the two situations clearly. Supercritical flow, flow. For the condition this is for the condition when delta Z is positive. Okay, Okay, there are some error. Can you hear me now?
Yes, yes, sir. Yes, sir. We can hear you, sir.
Okay,
Yes,
so
sir.
there was a network problem. It was reconnecting. Fine. Okay, so now we will continue. I'll open the set. Okay, can you see it now? Subcritical flow.
Yes, sir.
Y dash is less than Y when delta Z is positive. Y dash is greater than Y when delta Z is negative. When delta Z negative, you move towards right. So new Y will be now more than the original Y. Similarly, supercritical flow, when you move towards left, Y dash is greater than Y. Delta Z is positive. And when you move towards right, Y dash is less than Y, as you see in the specific energy diagram. Okay, so okay, so refer to the specific energy diagram. Refer to the specific energy diagram and you can get these things, set these things correct. Is that okay? Is this part understood? Come on, speak out. Is this part understood? Can you hear me?
Yes, sir.
Okay. So, no, see, if you interact, today there are 30 students. Okay, at least something good. Okay. So, okay. Now let's go to a small example. Okay. Water flows in a rectangular channel at a depth of 1.5 meter. A 30 centimeter high smooth hump produces a drop of 15 centimeter in the water surface elevation. Okay, so depth of flow is 1.5 meter and the hump height is 30 centimeter. Okay, and the effect is 15 centimeter drop in the water surface. Okay, so draw a neat figure and evaluate the here. If the drop is given, you can compute y dash. You can compute y dash because the drop is given. The new depth of water. How much will be the new depth of water? Y y dash new depth will be whatever you have the old depth. Okay, and I must deduct delta Z. Okay, I must deduct delta Z. Okay. Delta Z is 30 centimeter here. Okay. And in the post hump section, there is a 15 centimeter drop. Okay. So clearly, you should realize that the new depth of flow, see if y is 1.5 meter, then you deduct 0.3 and 0.15, and from 1.50 it becomes 1.05 meter. So new y dash is 1.05 meter. Okay, so y dash is 1.05 meter. Fine. So you should be able to compute the relationship from the specific energy expression. Okay, but the specific energy is not given. You cannot compute the specific energy here. You cannot compute angular channel E equal to this. Okay, so this is okay. So for E dash, I have Y dash, and this Y dash, if I have been given the the unit discharge, Q is given. Okay. So here you have been asked for what is the discharge per unit width. Okay, this has been asked. What is the discharge per unit width? Fine. Now, if discharge per unit width is given, then and y is known, y equal to 1.5 meter. Y equal to 1.5 meter. So if Q is known, I can compute, or bottom width V is known and discharge capital Q is known. Okay, in that case, I can compute the specific energy E, which is basically this is pre-hump specific energy. Okay, pre-hump specific energy, and I can also call this post hump specific energy. Okay, so pre-hump specific energy, if Q is given, I can compute E. Okay, and use the E and delta Z information to compute E dash. Okay, to compute E dash. Fine. And from E dash, I can now solve for Y dash, which is a cubic equation. Anyway, you are having an equation solver. You don't have to go for trial and error. You don't have to go for trial and error. You can get Y dash. Okay, that is what the usual question will be to compute or say by what is the, in that case, knowing Y dash knowing Y dash you may be asked for to find the change in water surface elevation. Okay, knowing Y dash you may be asked to find the change in water surface elevation. Okay, fine. So this is okay. But here water surface elevation is being given. So your E has not been given, Q has not been given. So whatever the Q is, there's a relationship between E and E dash. Okay, there's a relationship between E and E dash, and that relationship is E dash equal to E minus delta Z. E dash equal to E minus delta Z. So use this expression E dash equal to E minus delta Z and this part. Okay, so now this is your E dash. That is equal to so you are having E dash which is equal to E minus delta Z. E minus delta Z. Okay, so you know the delta Z, you know Y dash, and the only unknown is Q. Solve for Q. Solve for Q. Always provide the unit. Always provide the unit. Okay, so your answer should be Give me the answer. Send the answer in your group WhatsApp. Always I have said, write down the unit along with the answer. Which is you are writing in meter cube per second, meter cube per second, meter cube per second per meter. Okay. The same problem. If I give you B, if I give you B, say B is 10 meter, then discharge is 25.22 meter cube per second. Okay. Discharge is 25.22 meter cube per second. Fine. I can be fine. So here you get a direct solution. You get a direct solution for Q because you can simplify this, transpose these terms and get Q square into something is equal to something, and then straight away you can divide and take the square root Q. Okay, so this is a straightforward. You don't have to go for any solve button. Okay, you don't have to go for that. But when you are given discharge Q, then you compute E, then use E minus delta Z, compute E dash, and knowing E dash and Q, you have to find out Y dash, where that will be a cubic equation, and in trapezoidal channel it will be a fifth order equation, and you have to solve it by trial and error or maybe using the solve in your calculator the new flow depth y dash, or you can say post hump flow depth, post hump flow depth. Okay, y dash. Fine. So you can try some of those things. Now let's come back to our discussion. Let's come back to our discussion in the specific energy diagram. Okay? Are you having some class after this?
Yes,
Yes, sir. DPL sir is going to take class, sir. DPL sir.
People sir class is there.
Yes, sir. From 12 it's there, sir.
I'm not able to hear you.
Sir, from 12 it's there, sir.
From 12 to 12, sir. Fine. So
Yes.
we'll terminate it and we'll continue the discussion. So we'll start after we'll go for the discussion. For the discussion where we left, that is when the what is the maximum hump height which will produce no change in the offstream depth of flow. That is compute specific energy E1. Also compute the minimum specific energy EC corresponding to the discharge Q, and U1 minus EC is the maximum hump height delta Zm, which is no change in the okay. Now, as I was saying, one specific energy and 1 meter minimum specific energy. So 0.2 is maximum hump height, which will not bring any change in the critical the upstream flow depth. But now, if the hump height will become more than delta Zm, delta Z is 0.2, hump height is 0.3 meter, then specific energy falls to 0.9, which is not possible to maintain a discharge of or a the discharge of whatever the discharge. Okay. Now the discharge cannot change. So upstream specific energy will now revise itself or will now increase so that there will be a critical flow at the downstream or the post hump. So post hump specific energy will be exactly 1, which is minimum required. So now the upstream specific energy will change to 1 plus 0.3 to 1.3. Okay. So if the upstream specific energy will be 1.3, then downstream will be minus 0.3. That will be giving you exactly 1. Fine. So in those cases, upstream specific energy will change to 1.3, and as you move this vertical to right, you'll find in a subcritical flow, the upstream flow depth will increase. Upstream flow depth will increase. New upstream flow depth y dash will be greater than y. And if it is supercritical flow, new upstream flow depth y dash will be less than y. Okay, to maintain the new specific energy E1 dash. Okay, so we'll continue this discussion. We'll continue this discussion in the next class on Friday. Fine. So should we stop now?
Okay. Okay, sir.
Okay.
Okay, sir.
So we'll have our next class on Friday. Fine. Is that okay?
Yes, sir.
Bye. Bye.
Bye.